Good morning, good afternoon, or good evening, depending on where you're listening. Welcome back to AI and the Future of Work. Thanks again for making this one of the most downloaded podcasts about the future of work. If you enjoy what we do, please like, comment, and share in your favorite podcast app. And we'll keep sharing great conversations like the one we have for today. I'm your host, Dan Turchin, advisor at Insight Finder, the system of intelligence for IT operations, and CEO of PeopleRain, the AI platform for IT and HR employee service. We spend a lot of time on this podcast talking about data, how we get it, where it comes from, how it's used to build AI models, and what happens when it's inherently biased and leads to poor automated decisions. Today, we get to explore a different question. What if our approach is completely flawed? Maybe, just maybe, the answer isn't more data. Maybe AI can be human first rather than data first. Perhaps we can instead codify what small numbers of experts do to solve problems and maybe automate decisions based on that. It's a radical idea, but for certain types of problems like fixing industrial equipment, it just could work. Aitomatic is challenging traditional ideas about the role of data in AI and solving problems in the IoT or Internet of Things space, although the underlying principles apply equally well to a broad set of domains, everything from, say, aquaculture to carbon dioxide capture. Christopher Nguyen, Aitomatic CEO, is a Renaissance man and a serial entrepreneur. He's as comfortable talking politics as he is about neuromorphic computing. Christopher and a quite impressive team of AI engineers and research scientists founded Aitomatic last April following the successful exit they had of Aramo to Panasonic a few years back. Christopher received his doctorate and master's degrees in EE from Stanford and his undergrad from Berkeley. Among many other accomplishments, Christopher also founded and taught at the Department of Electrical and Computer Engineering at the Hong Kong University of Science and Technology. If you're not already, follow Christopher on Twitter at Pentagoniac. Thanks to our mutual friend, Tess Howe from Tess Ventures for the introduction. And without further ado, it really is my pleasure to welcome Christopher to the podcast. Christopher, why don't we get started by having you share a little bit more about your background and how you got into this space?
Thanks, Dan. Pleasure to be here. Well, you've covered quite a bit. So maybe I'll just start at the end. Right. So the journey that I'm on can be dated back maybe 10 years, the most recent one. After I'd left Google, I updated my LinkedIn and said that I wanted to work on something in big data / machine learning. And this was 2011, 2012. Big data was still a term that people were just starting to grapple with, let alone machine learning. So it didn't make any sense to anyone. But I had a podcast earlier around 2014, where I said the reason for big data is machine learning. And again, that didn't quite make a lot of sense to people coming from the big data side, but of course now it's an obvious fact. So I started a company to do the machine learning, or now people refer to it as AI layer of the big data processing, big data storage, big data processing, and the application layer. Long story short, we were acquired by Panasonic back in 2017, and by then we had built a product, and I'd like to refer to it at the time as a bunch of geeks with algorithms, right? Panasonic was about to celebrate its 100th year anniversary, 2018. It was founded by Matsushita-san in 1918. And we did not know this at the time, but the reason for their approaching us initially as a customer, right? We're very excited about Panasonic, NASDAQ, CIA, Kohl's, and so on as potential customers. But what Panasonic did was set up a bake-off, right, between us and a few other well-known companies to solve some of their industrial challenges, specifically industrial AI. But what they were really looking for was a team and a technology that could help Panasonic be part of that transition into the second century of the company. And the initiative can be thought of as software to hardware, but it's really moving up the stack, from a components player to somebody that can, control the user experience. Fast forward, after we were part of Panasonic, we remained our own unit. And so I helped with a lot of the global AI effort across the globe, the divisions. People may not know that Panasonic today is really an industrial giant, not so much in consumer electronics, but a lot in the industries. If you drive a Tesla, or you've seen a Tesla, the batteries in there are manufactured by Panasonic. If you fly and you look at the LCD screen and you enjoy Wi-Fi, 70% of the market share is Panasonic avionics. On and on, cold supply chain that gets a fish from the ocean to your the dining table. The technology there is provided by Panasonic and automotive and on and on and on. The genesis of Aitomatic came out of our initial failure being part of Panasonic, applying our machine learning algorithms to problems like industrial predictive maintenance, energy optimizations, and so on. We quickly ran into a very interesting problem. For this, we'll expand on it, but I would say essentially there is not enough data for machine learning in that context, and I can talk more about why that is. But it took us a while, 6 months to a year of beating our heads against the wall before we realized that there was, in fact, a lot of asset to be leveraged and to help solve the industrial AI problem. It just didn't come from data, but it turns out it comes from the domain expertise of the 250,000 people that are part of Panasonic, already. And so we developed something that today we call knowledge first AI. And that's, we left Panasonic and we launched the company back in April 2021. And we've just completed our first year of operation.
Let's build on that theme. I teased in the opener about human first versus what I'm calling data first AI. Why is that human first approach better suited for the problems that you're solving with Aitomatic?
Right. So one way to look at it is just to think about machine learning. You could say, given sufficient amount of data, right? And sufficient amount of compute, we could use machine learning algorithms to essentially discover virtually any pattern in the data. Put in a very crude way, very grossly, simplified way, machine learning can solve almost anything given enough data. But if there's enough data, is a big if. And it turns out in a lot of industries, and I've thought about this. This is any company that has a significant physical dimension, which is quite different from the world that I came from, and that most of folks in Silicon Valley come from, the Googles, the Facebook, the Twitters of the world that are digital first companies, right? There's a huge world out there, right? We still drive our cars, we still eat our lunches. We're still very much atomic beings, not just digital beings. And when it comes to industries that have a large physical component, right? We talk about industrial IoT, manufacturing, and so on. It turns out the question of having the right kind of data and sufficient amount of that data is a big challenge. Machine learning fails at these problems. I can give you a particular example of that, but there's a pattern out there, and very not just us that have discovered this. We're lucky in the sense that we're actually inside the belly of the beast, right? But a lot of vendors outside that try to sell to manufacturers and other industrial companies find that the algorithms, the machine learning algorithms alone will not work to solve these business relevant problems.
So let's take a specific example, maybe in the manufacturing space. Let's say a very sophisticated piece of HVAC equipment.
Yep.
And they're relatively speaking, like you've educated me about, a small number of, quote, experts on how to fix that HVAC equipment.
Yep.
And what you want to do is capture the sum total of knowledge of all the experts about how to fix particular problems that the HVAC equipment has and codify that.
Yeah.
It's a non-trivial problem. How do you go about capturing what's in this small number of, not trivially small, but relatively small number of experts' heads and codifying that in a way that you could then train models on how to recommend fixes for problems?
Well, let's talk about the motivation. Why do you want to do such a thing in the first place, right? Take the example you just raised, right? HVAC equipment. There's a field called cold chain, right? The cold supply chain that we work on quite a bit. That when we were part of Panasonic. Let's talk about predictive maintenance use case within that. In other words, in the past we have what's called reactive maintenance. When something goes broken, right? A sensor goes off, and then somebody goes out and say, okay, let me take a look. Oh, it's the compressor. And then there is preventive maintenance, which is an improvement, because reactive maintenance turns out to be very expensive. It's not the equipment you're worried about, it's the downtime, right? The downtime can be tremendously expensive, even in life critical situations. I don't know how you measure the loss of lives. So preventive maintenance essentially says, okay, every 6 months, let's go through and just replace this set of components so that they can't fail. The chance of their aging and failing is very low. The holy grail is predictive maintenance, which is fixing things before they catastrophically fail, but only those components that are needed, right? So you need to be able to answer the question, can you tell me the probability of this compressor failing over the next 2 months, right? To be able to do that. To be very precise, what that is failure prediction, right? Because predictive maintenance, a lot of the people that have implemented it out there or claim to have done so, they have not actually done failure prediction. What they have done is anomaly detection, right? And what anomaly detection is, and that can be done with machine learning with massive amounts of unlabeled data. And all that is that you take in as much temporal or time series data as you can. And then over time, you discover certain patterns that you would say, well, these are normal things. I've seen them before. And one day you wake up and the sensors are sending a series of signals that are abnormal. They're not necessarily alarms, right? But these are patterns you haven't seen before. Then you trigger an alert. You say, okay, I'm seeing something strange. That is useful, but it's not actually failure prediction. All that is something looks different. Not even something is wrong, right? It could be that, the power source is a little different today. So what happens is machine learning ends there. In order to then map that to potential failures, machine learning has to enter what's called supervised learning. In other words, there must be a lot of labels of past failures of the same type so that I can, okay, given this, then I can learn that. But the problem is what? Equipment is generally designed not to fail a lot, right? And then even when you have past failures, service personnel that goes out there and replace things, they tend to replace a lot of things. So if you look at the log records, it's not just the compressor, it's also the filter, it's also the temperature sensor and so on. So then you look at those things, they're not useful labels for machine learning. And yet when you give it to a human expert who knows that range of system, they will look at the sensors and they say, based on this reading, based on this pressure being too high and the temperature being too low, I think you should look at the compressor. So that's the original motivation of when we realize we need to talk to these experts, because we can only generate, using anomaly detection, signals that something looks different. It still requires a human expert with their domain expertise, with 30 years of experience, to look at the data at that time and then say, based on this, I believe the probability of failure A is this, failure B is that. It took us a while longer for us to essentially accept defeat, right? And say, okay, all right, we keep having to go through this manual process of asking the 3 experts that are available, in all of the country of Japan. Why not start to figure out how to codify whatever procedure or heuristics that they go through. And it was when we started doing that we began to succeed as a industrial AI unit. Right.
So academically, this approach makes sense. And I certainly see it from the perspective of building a business at Aitomatic. But if I'm one of the three experts, my reaction is I want to fiercely protect that tribal knowledge because I don't want to make it easy for you to automate me out of a job. How do you respond to that?
Well, these three experts are having to service all of Japan. So they're actually overworked. But you touch on something very interesting, right? There was a talk I gave at the 2000, I think it was 18 AI conference, O'Reilly conference in London. And one of the questions was, how do people feel about being automated away? Because, there's a lot of talk at the time, even now, about, masses of people, manufacturing, for example, being automated away by AI. What we do, and it turns out when we look across the landscape, most of the time it is about scaling the few human experts that do not have enough muscles and brains and time to go solve problems, that are at scale. That turns out to be the much bigger value creation for smart companies like Panasonic that know, what the points to leverage are. It's not so much about replacing, removing 10 relatively lowly paid manufacturing line people from their assembly line. So the use cases that resonate, for this kind of thing is very much about finding the cases where really only the human expert can solve, but you actually have so much deployment out there. And I think in the US, we may have talked about this in one of our earlier conversations. In the last 40 years, everybody's been encouraged to go to college, right? Nobody wants to do the trade work anymore. But it turns out trade work, maintenance, plumbing, tooling, and so on, that pays really, really well. So the world is in short supply of human expertise. And so what we're doing here with this knowledge first AI is to be able to apply that, at scale. But interesting physical problems for which machine learning with data alone cannot solve.
So when we think about future opportunities, problems that can be solved with AI and machine learning, what would you say is the biggest constraint on innovation? Is it compute power? Is it storage? Is it the limitations of how fast we can process signals? Is it human ingenuity? What is it that's holding us back right now?
Oh, I've been in technology for a fairly long time. When we started dating ourselves, when I said I worked on XNS, right, which is the conversion to TCP/IP back at Berkeley, I've seen a lot of these cycles. And the correct answer to your question is that it depends. The bottleneck or the long pole, if you're doing things right, you have a different bottleneck that sort of rotates every few years, every 10 years or so. In computing, we've got storage bottleneck, networking, communication bottleneck, or compute CPU bottleneck, right? Right now, where we are with respect to machine learning and AI, for example, for a very long time, it was a computing bottleneck, even though we didn't really realize it, right? And then in 2012, the Google Brain team published this work, that say, well, we're just applying this deep learning algorithm, which has been known for a very long time, to a very large compute resource that at the Google's disposal, and suddenly the same algorithm performed wonderfully in such a way that sort of accelerated and went right past all of the other machine learning approaches. Today, it may seem like we are also compute limited, right? But increasingly, people are seeing, well, there are a few institutions, right? A few players like a Google or a Facebook or an OpenAI that says we're going to train extremely large scale models. But the next breakthroughs, a lot of us believe, is going to be in somebody being smart about the way of doing something, right? And in the more generic sense, I use the word algorithm, but I don't just mean the machine learning algorithm itself. But for example, right, approaches or algorithms or ways to codify human knowledge, right? I think that kind of thing will allow us to make the next major leapfrog in terms of this broader field that we call AI, artificial intelligence. That is not just machine learning.
So I often get on my soapbox on this show and I talk about the importance of practicing responsible AI. And as someone who's hired many AI engineers, and I know you talk a lot publicly about the field of AI engineering, what do you think is our responsibility as, let's say, vendors or anyone who's putting AI-related technology out into the public domain? What kind of responsibility do we have to train AI engineers to be ethics aware?
Yeah. Strangely, that turns out to be a controversial question within the field. I regret that there are people in our field that say that is not the problem of the people designing or practicing these things. It's kind of like guns don't kill people, people kill people. I do think there's a shared responsibility, and I think that is much more than academic for people like us, because we do work on life critical systems. One of the things we do is automotive, both the in-cabin experience as well as automotive cybersecurity. Over the next few years, cars are going to be less like traditional cars and more like computers on wheels. They're going to get attacked, right? Cyber attacks is a very, very real thing, as we're seeing in during these times. There's a real war going on, physical war. People realize, okay, well, war is real. I think the number one thing is the first thing that companies like a Panasonic have always been concerned with, even before the latest wave of AI, right? When you build a car, you got to think through, okay, there's going to be humans driving in this thing and safety features and so on. So the responsibility on AI practitioners or algorithm designers, researchers and so on, I think is not any less. You have to think about the impact of these things. How you go about these things, there's a lot of debate about it. But I think the way I think about it sort of philosophically, or my mental model, is the following. We focus too much on intent. What matters is impact, right? Because by incorrectly focusing on intent, it allows people the out of saying, if I don't mean bad, if I didn't mean to do that, I'm okay. But I think if we're held accountable to an appropriate degree for the impact of our work, then I think we'll begin to have the right systems and processes for measuring these things and even regulating these.
You and I started talking about a recent guest that was on the podcast, Gordon Wilson, who's the CEO of Rain Neuromorphics. And you ended up drawing me on the back of a napkin a diagram of how potentially we could recreate the human brain in silicon. And it led me to be curious to ask you this question, which is, what gets you most excited in terms of research themes, potentially achieving some kind of breakthroughs that could dramatically accelerate the field of AI, maybe, similar to some of Hinton's research, a decade or 2 decades ago? Like, what's the next breakthrough that will be achieved in academia?
Do you mean AI or you mean in terms of human impact?
A lot of it comes back to, I was thinking more about, like, you were telling me about memristors and some things that we could potentially do with some fundamental breakthroughs. What's the fundamental breakthrough? Almost, I was thinking about it, like backpropagation or something that ends up being just a foundational technology that unlocked, deep learning. Like, what's the next equivalent of something like backpropagation?
Right. Well, you touched on what we talked about, right? Starting from the memristor as one possible such a device, but there's a whole area roughly labeled neuromorphics, right? Or let's call it human brain inspired computing. One thing to realize is that we went from CPU, which is a von Neumann machine. It's actually quite a very different, it's an unnatural invention, if you will, because the compute power we have is so little that we have to impose a lot of human knowledge, the programming from the outside, right? It's a non-learning computer, right? So we have this arrangement of compute separated from memory, and then they come together doing some processing and so on, right? And then we transition to this age of GPU, which happened to be, I would say, an accidentally useful computing unit, right? Because what a GPU does is that it doesn't generically do all the compute that a CPU does. It does the same kind of calculation, but across large arrays very quickly, which is a very useful operation for machine learning. And people get to be more efficient with FPGAs and so on. But I think the way I think about it is that all we're doing is we're simulating, right, the equivalent of a neuron, right? And I want to be careful because a lot of people say, you oversimplifying. We're really not building the human brain, but we're inspired by that. But the neurons units that we're using today is incredibly inefficient if you think about it compared to the human neuron, or compared to the basic unit that we want. All the neuron really does in this sense is that sums up signal from a number of inputs multiplied by some weights, and then has a single output coming out, and then trigger if it's above a certain threshold, don't trigger if it doesn't. That operation can be vastly more efficient, right? You could use for example, a single transistor to do it, or you could use an optical device to do it, or we mentioned the memristor. So the idea of going through from all of the simulation, right, of the neuron equivalent to something where it's a single device doing so very efficiently. I think we've learned in the last, really 100 years that anytime you multiply compute power by a factor of 10x, amazing things happen that you and I can't sit here and predict in terms of use cases. So I'm pretty excited about, let's say the compute cost of AI today going down by a factor of 1,000, right? Who knows what kind of intelligence that would unlock.
So let's say it's imminent, maybe in the next decade. What's one example of a behavior that will be commonplace in daily life that will be enabled by that breakthrough that would today just seem like science fiction?
I think probably the very obvious one, that is what is AI, right? It's prediction, it's anticipation. Everything else, all the compute we've had up to this point is generally looking back, right? And then doing the analysis of that. But the decision making, the modeling of the future is still very much the domain of the human brain, right? Of course, we're at this transition where computers are starting to be able to be relied on. Right. In fact, that's my business in terms of predictive maintenance. Right. Is this compressor likely to fail within the next 2 weeks? Right. With what probability? So I think that's one thing that computers will get much better at. Right. They will be able to model the future much better, and they will be able to predict likely outcomes. Right. 80% sure this is what's going to happen, and 70% it'll be this case. And depending on how we build them, maybe they'll be doing so much more rationally than the way the human brain does it, right? I mean, people don't realize how flawed, how primitive the human brain is. I don't like to think in terms of building, the equivalent human intelligence. It's just another track of smart machines, right? So I think the ability for machines to be able to anticipate our needs, our wants, our desires farther into the future and more accurately, I think it's going to be a very interesting set of applications.
So Christopher, time flew by. I got to get you off the hot seat, but I got to ask you one last question. Somehow it came up in conversation that you had a significant contribution to Unicode a while back, and you can share what that was. But my question for you is, given all of your many accomplishments as a researcher, a technologist, an entrepreneur, a professor, to this point so far, what do you look back on and say, that's my proudest achievement?
That's hard to say, but I think, referring to the conversation where I talked about Unicode, that was a remark where I said, I observed, and in fact, Well, I'll say shared that observation, and I'll share that I just shared such an observation, back in at Cambridge at Harvard, a few days ago. The most impactful thing of your work will not be whatever you think it is today. That I was referring to my work on Unicode, the Vietnamese part, the implementation of that. I did that work during my PhD, which was on semiconductor devices, right? And it was a hobby, right? I love working on that. I wrote Vietnamese keyboard software. I helped define the VIQR and the VISKEY standards and so on. But that was my hobby. That was my passion. It consumed most of my time. I just spoke to my former PhD advisor to sort of remind him that I was only working on his work, maybe 20, 35% of the time. That's an example where, now that I look back, the Unicode work is far more impactful than whatever I did with quarter micron BiCMOS devices, right? And most recently, I was on a trip to visit the Kennedy School at Harvard, where they have a new initiative called the Global Vietnam War Studies Initiative, and I'm helping to sponsor that. And I reminded the participants, right? I'm a supporter of that. The people that spearhead that the impact, we can forecast, right? Their goal is, I think, it's quite relevant to what's happening in Russia and Ukraine today. They're trying to promote through interviews, truth telling and healing, from of the wounds of that war. And I said, I fully support that, but I believe the impact of that will be much greater than anything any one of us here around the table can predict today. So that's how I think about the meaning of impact.
So, Christopher, we're out of time, but please share with our audience, where can they learn more about your work and about the work of Aitomatic?
Yes, so our website is probably the easiest thing to go to. It's Aitomatic. It's like automatic, but starting with AI. So aitomatic.com.
Excellent. Well, I look forward to having you back for another episode. There's so much that we didn't have a chance to unpack, but this is a great starting point. You mind coming back at some point?
Absolutely.
Good stuff. Well, this was really a pleasure. Thanks for hanging out, Christopher. Appreciate it.
All right. Thanks, Dan.
Well, that's all the time we have for this week on AI and the Future of Work. I'm your host, Dan Turchin, signing off, but we're back next week with another fascinating guest.